So we're given the graph of a function called f of x. And at f of x, there is a point called a, where there is a discontinuity, as you can see by the hole in the graph. So the question is, what is the hypothetical output of the function f of x at a? So in order to answer this question, we need to understand what the idea of the limit is. So let me show you. So the limit gives us a hypothetical value or hypothetical output of a function at a point using surrounding values. So what do I mean by this? Well, if we look at the graph right here, at the point A, the value is undefined, meaning that there's no numeric value attached to it. We can't really say what it is. So the next best thing is to say, okay, well, what is the hypothetical value? What would be the output if the point was continuous, if there was actually something there? Well, what we can do is that we can actually use surrounding points in order to answer that question. So in this case, if I look on the right here, I can evaluate this point. And at that point, let's say that this is like 2.01. And right here, let's say that this is like 1.99. And right here, maybe this is like 1.90. So by using surrounding values, we can actually see that these values, as you get closer and closer to this discontinuity, is approaching one specific value. And that one specific value in this case is 2. So we would say that at x equals a, the hypothetical output is 2. And this is the basic idea of the limit. This is not typically a traditional way of showing this, but we'll be diving into that right now. So here's the basic notation for the limit. This is what you're going to be seeing in every single calculus textbook from now on. So how we read this is that we start with the lim right here. So what the lim is, the way that we say it is the limit. So the limit, and then we go to the x pointing to a. So the x pointing to a is as x approaches a, the value a. So a can be anything like 2, 3, 4, whatever. And then the f of x portion is going to be equal to of the function f of x. And the equal L is basically going to be is equal to the value of L. So when we're saying everything, it's going to be the limit as x approaches a of the function f of x is equal to L, or L being the hypothetical output. And that is basic notation. So now that we've gone over basic limit notation, let's talk about basic requirements for limits. So right here, I have a bullet that says, in order for the limit to exist, the limit from the right-handed side as x approaches a needs to be equal to the limit from the left-handed side as x approaches a. So let's go through a couple of examples using this idea right now. So the first example that we have is that it says, find the limit as x approaches 3 of the function f of x using the graph of f of x. So the first thing we want to do when we're going through these graph problems is that we want to identify where the value that we're approaching at right here. So as you can see right here, we have 3, and this is the value that they want us to go to. The next thing we want to do is that we want to evaluate the right-handed limit. So the limit as x approaches 3 from the right of f of x. So if we look at the graph right here, as we approach 3 from the right-handed side, we see that our outputs of the function get closer and closer to the value of 2. So therefore, what we can say is that the limit as x approaches 3 from the right-handed side is going to be equal to the value of 2. Now let's look at the left-handed side. As you can see, as we get closer and closer to 3 from the left-handed side right here, we see that our outputs of the function get closer and closer to the value of 2. So therefore, what we can say is that the limit as x approaches 3 from the left-handed side for the function f of x is also equal to 2. And because based off our previous knowledge, we know that in order for the limit to exist, the left-handed limit and the right-handed limit need to be exactly the same number. And we see here that they have exactly the same number. So therefore, what we can say is that the limit as x approaches 3 of the function f of x is equal to the value of 2. And that is our answer. So we're given the following function of f of x, and the question is, find the limit as x approaches 4 of the function using the graph. So a little thing to know about the graph has intervals of 4 units that go all the way up to 8, and the f of x axis has units of 4 that go all the way up to 12. So the first thing that we need to do is we need to identify what point that we're evaluating around. So as you can see, it's asking for us to evaluate around the point 4, and that is right here. So the next thing we want to be able to do is that we want to be able to find the right-handed limit. So let's do that right now. So the limit as x approaches 4 from the right-handed side of the function f of x. So what does that equal? Well, as we get closer and closer to the value of 4 from the right-handed side, we see that the output of the function tends to trend towards the value of 8. So therefore what we can say is that the limit as x approaches 4 from the right-handed side is going to be equal to 8. Now let's look at the left-handed side. So the limit as x approaches 4 from the left-handed side of the function f of x. Well, as you can see, as we approach the left, we see that the values of the outputs tend to trend towards the value of 2. Tend to trend towards the value of 2. So what we can say is that the limit as x approaches 4 from the left-handed side is going to be equal to 2. Now, in order for a limit to exist, the right-handed side needs to be equal to the left-handed side. 8 and 2 are not equal. So what we would say is that the limit as x approaches 4 of the function f of x is going to be d and e. And what d and e represent is, it represents does not exist. So our answer is that the limit as x approaches 4 of the function f of x does not exist.